So how we go about modelling this, well, in the Hadley Centre, this is an old picture now of our supercomputer. We have a new one that we're just getting online at the moment. So what we have what's called a unified model. That is a model that is used for the weather forecasting, but we also run it forwards a long way into the future to look at future climate change projections. So it's essentially the same model. Slight differences because of the timing resolution and the timescales are different. The model's basically, it solves the mathematical equations of thermodynamics, fluid flow, gas properties, and it's very big. It's probably a lot bigger than that now. And there's many different output variables, so temperature, rainfall, some of the common ones, but there's lots and lots of others, such as plant productivity, soil temperature. So there's many more than the common ones that you would probably think of. And what happens is we split the globe up into grid boxes, both horizontally around the globe, but also vertically up into the atmosphere and down into the oceans. And we solve these equations across all of these grid boxes. So that's just a quick skip through how we do it. And the processes that we try and incorporate into these models, well, over the years, as we've been developing the model, it's been getting more and more complex. And we've been trying to add the main processes that we think are important for weather and climate. And so it started off with just atmosphere. And now we've got many different processes. We've got oceans, cryosphere, sea ice. We've got the carbon cycle, both on land in terms of trees and soil, and in the oceans in terms of plankton. And we've got the exchanges, for example, with clouds, volcanic activity we can introduce as well. So there's a lot of aspects to the climate models, and it's going really much more towards a whole Earth system model now rather than just a climate model. So there's a lot of validation and testing of the model that goes on, and just to give you an idea of why we think we're doing a reasonable job, at least at the large scale kind of global climate variables such as temperature. At the bottom here, the black line shows the temperature increases from observations that we've seen for global average temperature over the approximate since about 1860s. And the grey line shows, or the grey shaded area, shows what our model does when we include both forcing from greenhouse gases and other man-made aerosols, and also volcanic activity and natural variability. And so the reason it's shaded is because there are several different model runs. We don't just do one at a time, we do several different ones because this incorporates the variability that the natural system has. And so you can see that this captures the trend reasonably well. However, the nice thing with models is you can kind of take out one of the aspects. So if you take out greenhouse gases, this is what our models do in the grey. So they don't capture this recent rise in global average temperature. Likewise, if we take out the natural variability from, for example, solar cycle and volcanic activity, we miss out something around the 1950s, 1960s. But when we combine them, we have a very good relationship. So this is one of the forms of evidence that we show our models are doing a reasonable job. But there are always big uncertainties and lots of processes we must have missed out.